Okay, this will be the first lecture on CAM synthesis. The We will look at two things in the first part, which will be about possibly about two lectures as to why we need the CAM follower systems. We will motivate that in this lecture. And then we will look at the classification of CAM follower systems and associated nomenclature in the next lecture. Then I'll probably have about 2 to 3 lectures, maybe 2 to 2.5 lectures looking at graphical design using of CAM follower systems, and the another probably about 2 to 2.5 lectures looking at the analytical way to do the CAM synthesis. So with that, of course, the module 2 will be wrapped up, and then Dr. Abhijit Sarkar will take over for the rest of the semester. All right. So let's look at what is why do we need CAM follower mechanisms. So we have seen mostly the mechanisms where the output, if you looked at, was a rocker, in the crank rocker case, a slider which was going back and forth, or a full crank which was going through this. Sometimes you also had a coupler, but even there, the coupler was mostly involved in basically what is called as a continuous motion, which could be sliding or oscillating or whatever. But there are a lot of situations in mechanical engineering in industry we require the motion to be intermittent, which means there should be time intervals where the output link, which could be the coupler or the rocker, as the case may be, or a slider, it has to remain stationary for some time. And this is called as a dwell. Dwell simply means it is sitting there without moving, velocity and acceleration is zero, and then it starts to move from that particular position. The example for this is the opening and closing of IC engine valves. So here is the intake stroke of an IC engine. You can see that it is opening. It's already open. And so if you focus on this valve out here, it is already open and sitting there. Now you see it started to move and close. So it opens, closes. Let me back that up a little bit. Let me go back and start to play right from the beginning. You can see right at the beginning of the video, it starts to open and quickly reaches an open position, remains there for a substantially long period of time, and you can see towards the end of the downward stroke of the piston, it starts to close. So you can see now it is closed, and it will remain closed for the rest of the cycle. As you can see now, the piston is moving up. It is now moving up and the compressing the gas. We have towards the end, as it reaches the top dead center, we have combustion, and you can see the fire combustion happen within the thing, and the pressure expands rapidly and pushes the piston down. And as the piston will basically be in an expansion stroke, which is also called as the power stroke. And then it basically now starts to move up, and you can see that the exhaust gas, the valve on this side opened and is sitting at the open position now, and now you will see it will again close. It will move. Yeah, now you can see that closed. Okay, fine. So you have the situation where both valves have intermittent motion, the intake and the exhaust valve. Of course, piston is part of a slider crank mechanism, which is 1:1 ratio. So you see the IC engine thing is a machine which has two mechanisms. You have a cam follower mechanism, which opens basically the valve and the closes the valve, and you have, of course, a slider crank which allows the piston to go back and forth. All right. So now, how do you generate these dwells? It's possible to generate these dwells usually using coupler curves. It's not possible to do that with a simple rocker or a slider directly. So typically we require a coupler part to do this. So one way to do this is to say, well, I will synthesize first a 4-bar mechanism, and I will look for a part of the coupler curve that is approximately circular. So here I will highlight that. So here I have designed basically a coupler curve. So you can see that in this part of the coupler curve, essentially it is almost circular, and the center of curvature will be somewhere there. Okay. So the idea is to introduce a revolute joint at the center of the circular arc. So you have a circular arc. So if I now put a revolute joint at the center of this circular arc, then as the now join this joint which is at the center of the arc to a point on to that point on the coupler which is tracing a circular arc, then effectively what you have is that as it rotates through this will behave like a fixed pivot, at least for that limited motion range, right? So therefore what we do is we basically come up with an output diode. One of the links is from the coupler point to the center of the arc, and the second link is from the center of arc to the fixed joint. That's what I do. So here I have joined this. So since this is the center of curvature for this portion of the curve, S will not move. And then of course I join this to complete the 6 bar mechanism to a fixed joint. So now let's see how does it behave. You can see that as it comes through the circular part, N goes through the circular part, S remains stationary. Pay attention. Of course, for a very brief time, most of the time it is moving, but you do see that it is stationary for some part of the N moving through a circular curve. Just watch it. Yeah, it remains stationary. Now it starts to move. So once it goes past that circular arc, it starts to move. All right. So you could also generate this dwell through by so one type we saw was where we have it as the coupler curve as part of a circle. The other possibility is to use a straight line, which is sketched here. So you can see I have a coupler which is a curve which is almost a straight line. So if I were to now join, if I were to look at this point K, as it goes, as the coupler goes down this line, you can say this distance is going to remain the same, and therefore this will remain stationary. So that is another way to do this. Let's show you that. So that is what you have designed. Pay attention to the blue curve. Now K reaches the extreme, and you can see that it stays put there for some time, doesn't move, and slowly then moves once it crosses that. So there's a small segment on the coupler curve where K remains stationary or is in dwell. Okay, so this is one possibility. So you can do single dwell 4 bar, 6 bar. You can also use sliders to do a double dwell mechanism, which has been done by Norton, and there is this example. So you can see that here. So these you can see that the two curves, so it remains stationary here, starts to move, and then remains stationary at the other extreme position. So this is another example of a double dwell mechanism. The while it is possible using the coupler curves to basically generate single dwell, double dwell mechanisms, one of the major problems with this is it's not very easy to design this, either through the graphical method or the geometric design is quite intensive, not quite easy to do. Of course, you can take resort to analytical methods to do this, but that is also quite involved. So then the key question is there a better way to do this? And they do exist mechanisms called cam follower mechanisms, which involves higher pair joints. They provide the ability to get the kind of dwell motions, and can also control these dwell motions more easily, but they are difficult to manufacture. So these are used in machines. We saw already an example of a valve where we saw dwells. It's actually done through a cam follower mechanism, and it's much easier to synthesize given a specific output function when compared to linkages. But again, they are more expensive to make. But bottom line is that they are more compact, even though they are more expensive, much more compact and more flexible in the design characteristics that I can bring in. Now, this higher pair mechanism could be thought of as a degenerate 4 bar linkage, and whose link lengths are basically changing with various configurations, and therefore this varying link lengths is what gives it the ability to generate complex motions, right? And the cam follower as a higher pair joint, let us examine the mobility of such a cam follower system before we move forward. Before that, let's look at some pictures of cams and followers. The top is actually a camshaft of a 3-cylinder engine. You can see 2 cams here, or maybe it's a 6-cylinder engine. So no, this probably is a twin cam. So therefore, you can see two pair of these over here, here. There are 6 of these, and then the phase between these, the angles between these is dictated by the firing order of the engines. And this is a kind of an indexing mechanism. So you will see that this particular part basically rotates and then remains stationary, then rotates. So this is used for tool indexing in machine tools, for example. This is a follower, roller follower. This is the bearing on which the roller follower is based. This is an overhead cam example where the cam directly drives the follower, which is the valve here. Or you can have a rocker arm. The old style engines used to have a rocker arm. So the cam will actually actuate the rocker arm, which is basically pivoted here. So this is another link, intermediate link. And this link is in contact with the valve, which actually pushes. So you have this oscillating back and forth. So the cam moves it up, and then this rocker basically rocks, as it's called a rocker arm. It rocks about this pivot here. So you have an additional part. So that has been eliminated in most modern engines. You have a direct overhead drive, and this is another configuration where you can have the valve being opened through a separate push rod mechanism here. So this is only a rocker arm. You have a push rod mechanism with a rocker arm here. So all depends on as I said, the push rod rocker arm kind of design is an old design. Today you will see more of the direct design that is out here. All right, so some pictures just to get you familiar with what a cam and a follower looks like. We mentioned that it's a degenerate 4-bar linkage, so we'll pay attention to how we can find this so-called equivalent linkage. First of all, what do we mean by an equivalent linkage and how do we find this out? So it has a higher pair that happens at the contact between. So if you go back and see that picture, you see the contact here between the cam and the follower. So this is a direct contact. That contact is basically a line or a point contact, um, which makes it a higher pair. The idea is to replace this with an equivalent linkage with only lower pairs. So when we say equivalent linkage, we know that the cam and the follower at the point of contact basically is a higher pair mechanism, higher pair joint and higher pair, and therefore, but the mechanism becomes a mechanism with a higher pair. But we want to replace this with an equivalent linkage of lower pairs. When we say equivalence, what we mean is that when we look at the cam follower and look at the equivalent 4-bar mechanism or whatever that we are going to construct, the lower pair mechanism that we are going to construct, kinematically they are equivalent, which means that the velocities, accelerations are going to be identical. But please keep in mind that this is only for that particular configuration or position. We look at an example to just to describe how we construct this equivalent linkage. So let's take two arbitrarily shaped bodies, which I will call as a more, I keep calling potatoes, but they probably more look like some kind of a squeezed onion, whichever you want to call that. So this is body A is rotating about OA and body B is rotating about body 3, and they're contacting each other at this point P at this instant. So so this is the so the higher pair comes from this contact point P. So you can see from Kutzbach equation, there are a number of bodies. There is one fixed body. You have 2 and 3 which are rotating against each other. So n is 3, and number of joints, lower pair joints, are the 2 revolute joints corresponding to the rotation of the 2 bodies at OA and OB. So J1, which is the number of single degree of freedom lower pairs, is 2. And there is one higher pair which is at point P, which is the contact point. So if you work out the mobility works out to be 1. So how do I construct this equivalent linkage? So what we do is at the contact point, basically we draw at the contact point, we draw the common normal between the two bodies. So this is drawn. And now A is the center of curvature of the body 2. A to P is the radius of curvature. So the body appears to be rolling at this instant with this radius. Similarly, the body 3 has a radius which is BP, so it's part of a circle which is rolling at this instant with a radius BP. So we join, so OA to A is like the input. If I assume 2 is the input link, input body, so then OAA is the input link. AB becomes the coupler, which is the common normal. and P is of course the contact point that is there. OBB is the output link. So this is the equivalent. The right side we showed the equivalent stuff. So let's now look at it at a different contact position, right? So they have rolled against each other and they are now in this configuration. So you can see that the contact happens here. The common normal is like this. Now both A and B, the centers of curvature are on the same side. So we do the same thing. We join OA to A. So you can see that the input link has now become much longer. The coupler has become shorter, AB, and of course the contact point is somewhere there. And OBB is this line. So this is the new 4-bar mechanism that we have for this configuration. Alright, so this is how you will construct the equivalent linkage. I'm just showing this for a typical cam follower. That was two arbitrary bodies which were rolling against each other. Now we are looking at a cam which is like this, and the equivalent linkage, when we do this, this is often termed in textbooks as a half joint. The higher pair is basically it's replaced by a equivalent linkage. We call this as a half joint. So the center of curvature of the cam is out here. The cam profile is out here. The center of curvature of the follower, which is a circle, is out here. And remember that this point is basically this follower is translating back and forth. That's what typically happens in a cam. You could have oscillating followers also. So the effective linkage is out here. So you can see a dashed line representing the input link. This to this, between the two centers of curvature is the link 3 or the coupler, and of course the 4 is a slider which is basically a link of infinite length. So we have a equivalent slider crank mechanism. So one can replace, and this of course will keep changing, the dimensions will keep changing as the cam rotates. So some comments before I close. The first thing to look at is the link lengths are quite different at the two positions of the equivalent linkage. But keep in mind, one of the great advantages or the flexibility of the cam follower comes from the fact that these link lengths are variable. So this provides us flexibility to synthesize cams for different output motion requirements. But if I were to use this equivalent linkage method to do higher pair mechanism analysis, it is very time consuming. As you can see, I have to look at for each configuration. Let's say even if I take 10-degree intervals for each of these configurations, I have to find the center of curvatures for each of these, then come up with the equivalent the dimensions of the equivalent 4-bar linkage, then calculate the velocities and accelerations, and I have to do this for every 10 degrees. So this looks like a very tedious process, and it is. So then the question is, why are we even discussing this if we are not going to do this? And there is a reason for this, which will become very, very clear as we go along. This equivalent linkage visualization has its benefit in deriving the cam profile, analytical cam profile equations, as we shall see later. Okay, so we will come to that in the next lecture. In the next lecture we are going to see the classification of cams and also some terms associated, or cam language as I call it. Okay.